In our continuing discussion of the second law of thermodynamics, we want to take a look at the concept of order, probability, and statistics as it relates to the possible outcomes a system can achieve as a result of going through a thermodynamic process. In a previous session, we defined the concept of entropy and said that what's important is the change in entropy, delta S, which can be calculated by the heat, Q, divided by the temperature at that process. And as long as that change in entropy was positive, this was an indication that that process would naturally occur or was a naturally occurring spontaneous process. We mentioned that the reason for this was that in going towards more disorder allows for a greater number of probable outcomes than in proceeding towards order. So we want to discuss that just briefly here. We can do that in the concept of looking at the flipping of pennies and say, imagine that you have 2 pennies, and what are the possible outcomes in the case of having 2 or 3 or even 100 pennies? What are the possible outcomes? Well, you know that for 2 pennies, you can have either flip them up at the same time, and they can either come up with two heads or 2 tails. So there's only one choice for each one of those, whether it's 2 heads or 2 tails. Or we have 2 possibilities for heads or tails, 1 head and 1 tail, or the other one head and tail. So of the outcomes possible, we can either have one where there's 2 heads, one where there's 2 tails, or 2 outcomes where there's heads and 1 head and 1 tail. So which one is more likely? Well, the odds of getting 2 heads is 1 out of 4 possible outcomes, 25%. The odds of getting 2 tails is the same, 1 out of 4, 25%. The odds of getting 1 head and 1 tail is 50%, because you have 2 possible ways of getting that. And so here we have 1 way to get 2 heads, 2 ways to get a head and a tail, and 1 way to get 2 tails. So in this case, the outcome, the more probable outcome, is the one that has the most, numerically, the most number of ways of getting to that outcome. Well, let's increase this to 3 pennies. Again, with 3 pennies, there's only one way to get 3 heads. They all come up heads, or they all come up tails. Only one way to do that. But notice there are now 3 ways to get heads and 2 tails, or 3 ways to get 2 heads and a tail. Okay? Now, if you're counting on 3 heads coming up, you're only going to achieve that 1 time out of 8 possible outcomes. Same thing with the tails. But if you're counting on 1 head and 2 tails, there are 3 ways out of the total 8 to get that. So the more likely outcome is 1 of one type, head or tail, and 2 of the other type. That wasn't supposed to do that. Okay. In fact, the calculation of the number of outcomes for each particular scenario is a simple binomial calculation where capital N is the number of pennies you have and little n is the number of the desired outcome. For instance, if you want 3 heads, then little n will be 3 and capital N will be 3, of course, with 3 pennies. And if you plug those into the factorial expression there, you will find out that for capital N of 3 and little n of 3, You end up with 3 factorial over 3 factorial, which is just simply 1. And you have one outcome occurring. Okay, now what we're getting at here is that as you increase the possible number of choices for the system, or increase the number, in this case, pennies or particles, the number of possible outcomes grows dramatically. For instance, if you had 50 pennies, the chance that you would get 50 heads or 50 tails is exceedingly small. Exceedingly small. However, the chance that you would get 25 heads and 25 tails would turn out to be the most likely outcome, and there are a great many of ways that that can happen. And you would calculate that by letting capital N equal 50 and letting the small n equal 25, and then doing the calculation on the previous page for the number of ways that you could get 25 heads out of a toss of 50 pennies. And so what we're getting at here is that the reason that this system goes to that state in which there's the most diversity of outcome, the most number of different values for these, in this case, 2 different possible outcomes, either head or tail, is that that is where there is the greatest number of possible occurrences. In other words, you will get the greatest number of occurrences of 25 heads or 25 tails, as opposed to 50 heads and no tails. There's only one way for that to happen. So the system is going to be in the state that is most likely to occur. And as you increase the number of particles or pennies to 100 or 1,000, what you ultimately find out is that in order to, for instance, have any chance of having the system go to one of those very, very, very exceedingly unlikely states, there simply hasn't been sufficient time in the age of the universe for that to occur. And remember, it really is irrelevant because every roll of the dice is a unique situation again, and it's not a cumulative effect. So this concept of order and disorder as it relates to entropy really goes to the matter of what is the most likely state. Well, the most likely state is the one where there is the greatest number of ways of getting to that state, and in that case it means it's the most disordered state. So natural processes tend toward those states that have the greatest number of chances of getting equivalent outcomes. In other words, there are more ways of getting 25 heads and 25 tails than there are of getting 50 heads and no tails. For 4 pennies, there are 6 ways to get 2 heads and 2 tails, but only 1 way to get 4 heads. For 50 pennies, notice there are 12.6 million ways to get 25 heads and 25 tails. 12.6 million. There's only 1 way to get 50 heads and no tails. So given the odds, 1 or 12.6 million, what do you think is going to happen? So once again, gets back to the idea that entropy is a measure of disorder. There are more of those states available, the states that have the equivalent outcomes of the greatest number of possibilities is the state which will occur, and that is the state in which the greatest disorder is present. Natural processes will tend toward increasing disorder, and as such, disorder means a lack of predictability. And you can think about that in the sense that if you confine the gas in the room you're presently in, it's spread out in that room, but if you confine it to a small corner of that room, those gas molecules are more ordered, more predictable as to where they're located in that volume than when they're spread out into the entire room. So if you think about if you uncap a bottle of ammonia in a room, why is it that that ammonia doesn't simply stay around the bottle, but in fact ends up permeating the entire room and you can smell it quite quickly? And again, that is a consequence of the concept of entropy. That is, there's greater disorder for those ammonia molecules to be spread out in the room as opposed to being confined to some small region of the room. So those states that have the most order, in that case the ammonia molecules, those states that have the most order are those ones that are least likely for the system to end up in, and those with the most disorder are the ones where the system is most likely to end up in. So as I mentioned before, you can answer this question now: would conservation of energy allow the process where a cup of hot water sitting on your kitchen table would suddenly freeze? And as you know, the answer to that is conservation of energy would allow that. The fact that you never see it is the consequence of the second law of thermodynamics. It doesn't happen because the frozen liquid represents a more ordered state than the liquid, and therefore there are many more probable states for the system to be in the liquid state than in the frozen state. Therefore, it is not going to spontaneously freeze. It is actually going to warm up and the molecules move faster. Lord Kelvin incorporated the concepts of heat flow and entropy and the Carnot system, and he showed that the ratio of Q over T, which we've used in a previous discussion, Q over T was actually a very important state function. By state function, what we mean is this. You recall looking at a pressure volume diagram. And if you think about going from one point in a cycle to another point, there are many ways to go between point 1 and point 2. And if in going from point 1 to point 2, the path makes a difference as to the value of a quantity, then that is not a state function. State function is something that doesn't matter how you get between point A and point B, just simply the values of that function at point A and point B are dependent upon the endpoints. For instance, the potential energy change in lifting a book from the table up 1 meter is calculated by multiplying the weight of the book times the position of the beginning and the position at the end of that process. And it doesn't matter what we did to the book in between, whether we carried it around the room or not. Our calculation of change in potential energy is just simply the difference in the endpoints times the weight of the book. And that is the work that we had to do on the book. So there's a state function that only depends upon the endpoints. Well, Kelvin found that the entropy was also such a quantity that did not depend upon the pathway between the change, but simply depended upon the endpoints. And therefore, it became an important quantity, this ratio Q over T, and it was given the name entropy to somewhat make it look a little like a concept of energy, which is where the En comes from. Okay. And this change in entropy became a measure of whether a reaction was spontaneous or not. Recall that we've already mentioned that for spontaneous reaction we must have a change in entropy which is greater than 0.